Start. Okay. Wait. Nothing to review because you did the test, which I haven't marked yet. I wish they were marked. They're not. Today we're just going to keep going through, I almost said trig functions. Can you imagine? What? We're doing trig? No, we're not. Not yet. And I'm going to try to do as little as humanly possible. I did talk about it last day, but we're just going to breeze through section 4.5, which is on the graphs of logarithmic functions. The main takeaway being the domain of a log. So I guess that's kind of a review. The domain of a log of a logarithmic function the log of x. You know what? I'm going to specify. So when I write, sometimes when I write log of x, I mean log base any b of x is x has to be greater than 0. Okay? You can try it on your calculator, try the log of 0. You're going to get nothing. Because what does that mean? It means that b to the power of something would have to be 0, and there's no way to get there, right? B has to be some positive base, and so can't get 0. And so we're going to look a little bit more at just the graphs of these logarithmic functions, but we're not going to worry too much about it. Okay. Let's see here. Skip ahead. We'll just talk about some of these features. So if we have some log any base b of x, then the graph has a horizontal intercept at 1, 0, right? Meaning that, right, 1, 0, when x is 1, the output is 0, right? Anything to the power of 0 is 1. Right? And so I'll make a note here. Maybe I'll try to make this a little bit bigger even. All right. This is because log base b of 1 is 0, since b to the power of 0 is 1. So that's a fact. Right? If you try to take the log of 1, you'll get 0. Right? Which means it's going to pass through on our, I'll do a rough sketch here. It's going to pass through at 0, 1. So we know that much so far. Maybe I'll do that. 0. Oh, it said 0, 1. But I meant 1, 0. Makes a huge difference. Still waking up. The graph has a vertical asymptote at x equals 0, meaning that it's never going to touch x equals 0, right? But it's going to run along it and head to positive or negative infinity, depending on the transformation of the log. And so this is kind of untouchable here, x equals 0. And it's for that reason that we can't take, there's nothing that we can take that gives us 0. So we can't do b to the power of anything to get to 0, because b can't be 0. What else? The graph is either increasing, the graph is increasing and concave down. So we'll start with the concave down. Concave down is going to look something like this, right? You've got your cup facing down, and then it's increasing And that means it's going to look something like, oops, come on, like this. We already established that the domain of the function is x greater than 0, or from 0, not including 0, right? That's important that you put that round bracket there. Oops. Up to infinity. And then the range is all the y values, is all real numbers. So from negative infinity to positive infinity. So this thing is going to look a little something like this. It's the log base b of x. We can transform this thing just like we've been transforming other functions, but like I said, we're going to kind of breeze through it because, well, why not? Let's see here. There's an example I wanted to do. Probably in the example, chapter 4 examples. Make a little note. Oh. Copy. We have to find the domain of y equals 5 plus the natural log of 4 minus 3x, right? We add that we can't take the log of 0 or a negative number, and so that we add it to the list of we can't divide by 0 and we can't take the square root of a negative number, right? So we're just building out our things to look out for. So this 4 minus 3x has to be greater than 0. Right? The other portion, the 5 plus 5, can just be 5. That's fine. So it's only the inside of the log that we're concerned with. Yeah? And so 4 minus 3x has to be greater than 0. Now for me, I like to take this, and there's lots of different ways that you can approach it, and hopefully you'll end up in the same spot. But I like to solve for where 4 minus 3x equals 0. And then I use little test values to figure out where it is greater than 0. Okay. So I'm going to use 4 minus 3x is equal to 0. Right? If you're comfortable with inequalities, right, making sure that if you're dividing by a negative number, multiplying or dividing by a negative number, then you have to switch the sign, right? So you want to be really careful. So that's why I like this method, and then I can figure out later using test values where it's supposed to be. So I'm going to add 3x to both sides and then solve for x, which is going to be 4 over 3. Okay. So then, right, this is where it equals 0. This we notice is a line, right? Y equals mx plus b. So this is a linear function. So it's either going to look like this or like this. We have some idea already, right? Noticing that the slope is negative, right? So it looks like I'm going to be sloping downwards like this, right? But on a number line, what I'm going to do is just put 4 over 3. And my trusty calculator. Let's see here. Gonna go with test value of 0, my favorite. And why not 2? So then what I'm gonna do is I'm gonna take 4 minus 3x at 0. So then I have 4 minus 3 times 0 is 4, which is greater than 0. And if I do the same thing on this side, 4 minus 3 times 2 That's going to be 4 minus 6, which is -2, which is less than 0. So that's bad. You could also think of it as, okay, so now instead of this number line, make this number line your x-axis. Or you could think of it like this. Now you've got your x and you've got 4/3, right? This is still a line, 4 minus 3x. We figured out where it equals 0 is at 4/3. And then we can draw this line. Starts here at 4, right? When x equals 0, y is 4. And then we've got a negative slope of 3, but I already know it's going to cross the x-axis here. And so I can just draw or sketch a line through those points. Right? Usually you wouldn't have to do it. You wouldn't have to draw it out like that, but just in your head, knowing how functions behave and what they look like, right? You could figure out that, oh, okay, if I'm starting at a positive intercept and I have a negative slope, then everything between or everything less than 4/3 is going to give me a positive value, which means that the domain remembering that you can't be equal to 0, right? That's a key thing. So you have to exclude 4/3 and every value up to not including 4/3, which we show with a round bracket. So I'll highlight that because that's important, right? If you put a square bracket, you're saying including 4/3, but that's not in the domain. So even though we used it to figure out where it crosses between positive and negative, it's not in the domain. Nice. Yeah. Oh, this one? Yeah. It's from here. So this tells me that the y-intercept is 4 and the slope is -3. Yeah, so the key is recognizing that this is the equation of a line, right? Yeah. Yeah, if you just have one x, it's a line. Yeah. Someone? Let's see here. You could do something sneaky and you could add 3x over here. You're saying if you wanted to work with this inequality? Oh, so I moved. I added the 3x over here to get rid of the negative. And so that would be the difference. Yeah. No worries. Okay. We can do transformations of logs, obviously, because we can transform anything, but sorry, was there? No. Sure. Let's see here. We're going to use Desmos to sketch this because I'll never ask you to sketch anything again. I feel like I've asked you to sketch stuff before, but I'm not going to do it again. Sketching helps. Yeah, it helps you visualize the problem, and that's why it's pretty typical to make you do it. But we're going to use Desmos for this one. Let's see here. I want to try to do that thing where I show you both my screens. Yee! Okay, so 4 times the log, which is one of the functions, the common log of 5 times x plus 2. And that's good. Okay. So this can grab some key components here, is what this graph would look like. Okay. Clearly still a log graph, right? It's got that same shape, but it's been shifted over for sure to the left, but also, right, it's been kind of shifted over. Looks like it's been shifted over the word vertically as well. Let me take a screenshot. Oh, let me keep these points on there. Save. We can bring this in so we, oh, come on. So we can draw on it. Okay. So now, right, we have a different y-intercept. In fact, we have a y-intercept, which we didn't have before. We only had a horizontal intercept, right? And so it looks like, well, we know it should be passing through 1, 0, right, from before. So it's definitely been shifted over this way, which would shift your vertical asymptote, right? And so without anything further, we can rewrite the graph, any log transformation. Let me grab this in here. So any transformed log function can be written in the form a times the log of x minus b plus k, or a times the log of negative x minus b, and then plus k if it's horizontally reflected. And then we know that x equals b is the vertical asymptote. Okay? So notice the structure here. Inside the log, you have something in terms of x minus b. Okay? So what we can do is we can look at this here and we can say, okay, I've got 4, which looks like it could be my a. Right? I've got the log of 5 times x plus 2. But what I could do is I could rewrite x plus 2, right? X plus 2 is the same thing as negative 2 negative x minus 2. Because when I bring this in, x plus 2. Okay. Which means were we ready? I think so. Okay, so starting at 4 times the log, we'll go for it. I'm hesitating. Can you tell? Okay, fine. Negative x minus 2. I don't like that negative x there. Or, yeah. What can I do? This negative, I can rewrite as -5. But I can't take the log of a negative number. Where did I go wrong? I did something weird. And also, his notes don't match his textbook right now. And that's weird. Like, hey, x plus c. Let me just try something. No. I knew I didn't want to do this one. Okay. Let's skip this. I don't want to do it. I want to talk about half-life instead. I know, and I'm not going to make you do it, and it's not coming to me, so.
You're not testing on this anyway?
Done. No. I'm not a monster. Sorry, guys. Just one of those mornings. We were just talking about it in the office, how everyone was like having a weird morning. Steve tried to make a latte out of cat food, and Joy like found herself in the bathroom filling up her coffee maker thing, and she's like, how did I get here? I'm like, I do not want that day. But it sounds like I'm kind of getting that day. 4.5 is finito.
The other one, it was 6 in the morning. I'm so tired. I'm like, I gotta charge my phone.
It's the day. Something about today. Yikes. Okay. No clue. No clue what's going on. We're going to talk about half-life and doubling time, which something tells me you've seen potentially maybe in chemistry or something. Not yet. Haha, what a win for me. Okay, great. So half-life of, well, anything that decays or deteriorates is the time it takes for half the substance to decay, right? And so that's useful information, right? And so let's skip straight to an example. We were supposed to do that, but I'm not going to, because I guess I can't. I don't know. I can't. Just not right now. A radioactive substance decays following this equation, 100 times e to the negative 0.036 times t. Find the half-life. Yeah. So in order to find the half-life, right, we want to find the t that it takes for 100 to get to 50, right? And so let's see here. Let's make a little note. We want to find the t that makes 100, which is the initial value, which is kind of baked into the equation, right? We know that this is our starting point, regardless of if we're decaying or if we're growing, right? And so 100, the initial value, go to 50, which is half of 100. Right? I say that because the math isn't always that breezy, right? So then you would do 100 divided by 2 and figure out what it is. So what we want to solve is we want to solve 50, right? The output or the amount left has to be 50. So I'm going to force that to be 50. And then I have 100 times e to the negative 0.036 times t. And I want to solve for t. All of a sudden, we're back to something that we know how to solve already. You had to do it on the test. And so what's the first thing we're going to do is we're going to get the exponent on its own, right? And so we have to divide over by 100. And I'm going to put it on a fresh page here. 50 divided by 500 would have made a mess. E to the negative 0.036 times t. 1000. I made a mess anyways. Oh, everyone just go home. It's game over. Especially me. So now, usually I would write 1/2 to emphasize that it's a half-life, right? But let's just do 0.5 for space reasons. So 0.5 is e to the negative 0.036 times t. Now I'm ready to take the log, any log of both sides, right? But I'm going to choose the natural log because I've got base e here. And if I take the natural log, then one of the sides will cancel and I don't have to deal with logs on both sides. So here, this tells me to use the natural log. I have to do it on both sides though. The natural log of 0.5 and the natural log of e to the negative 0.036 times t. Now, as you get more comfortable with this, right, I would be okay with you just writing negative 0.036 t. That's quite a leap from here, right? As long as you've shown me that you've taken the log of this side, then I understand that you've taken the log of this side, and the natural log of e is 1, so you don't have to write out all those steps, right? So here you could have skipped to this point, and I'm entirely fine with that. Right? Because we've used the log laws so much now that it's okay. We know that the natural log of e goes to 1, and then the reason we take the log is to bring this power down, right, down in front. And so we have those skills now. So that's good. It's what we were working on. All that's left is to solve for t now. Right? I'm gonna do my my switcheroo. I'm gonna bring this kind of my revolving door, right? And say that t is the natural log of 0.5 divided by negative 0.036. The natural log of 0.5 is just a number. Let's see here. Natural log of 0.5 divided by negative 0.036 puts me, unless I did something weird, at 19.2540885. I don't know what. The log of anything less than 1 is going to be negative, so those negatives would cancel. It doesn't say what time, so there's no units given, but that's okay, we found it. t is roughly 19.25 hours, minutes, whatever, doesn't matter. Good. The half-life of iodine 131 is 8 days. So now we're told what the half-life is, right? Which means that, right, this was the half-life of the previous function. So now that's telling us that t, when t is 8 in this equation, right, then we have the half-life. Yeah? And so we want to find the annual decay rate. So let's start with just a broad function. And I'm going to assume it follows the continuous decay rate. Fair assumption. It's continuously decaying. It's not just decaying, decaying, decaying. So where I'm going to start is I'm going to say f of x is a times e to the k times x, right? Where k is going to be the value that we want to find. And so, right, this is the annual decay rate. Or I'll say k equals, just in case my arrow's bad. Okay. So, believe it or not, George isn't at home. When x is 8, I have half of what I started with, right? And so here, this is going to be 1/2 a. Feels weird, right? But let's try it. 1/2 a, or maybe I'll do a divided by 2 just to clean things up a little bit, right? Same method as before, it's just that we had 100 and we were able to figure out what the value was. But regardless of what a is, right, I can say that, okay, a, the half of a is a over 2.
Let's go straight to 1/2. Get rid of the a in that one. We're not solving for a.
Yes, you can. I'll show you why. But you could, yeah. Yeah, if you're working through problems, you're allowed to. I just want to show you why. So then times e to the k times 8. Right? Because this tells us that f of 8 is 1/2 times a. Okay. What can I do? I could multiply over by 2 and divide over by a, and then divide over by 2 again, right? And so there's a little bit of kind of trickery going on here. I'll do it step by step. 2a e to the, and I'll write 8k just because it's a little bit nicer to read. Now I'm going to divide. So I multiplied over by 2. That's all I did in that step. And then I'm going to divide over by a. So I get a over a is 2e to the 8k. A over a is 1. So I get 1 is 2e to the 8k. I can divide by 2 again. Bring it back over. 1/2 e to the k, because I'm trying to solve for k, right? So I need to get the exponent on its own. And so now I'm ready to take the log of both sides, right? But here, notice that it's just 1/2 and then e to the whatever 8 times the decay rate. Yeah. So again, if you're comfortable, I would love to see this part where you show me that you understand that the output has to be half of where it started. But then if you jump straight to here, that's fine. You could just look at this and say, oh, I've got an A here and an A here, right? They get rid of them. So from here, you're allowed to go to here if you want, right? Or you can follow the steps and that's safe too. Wow, really can't draw arrows today. There. Now we can solve for k. Again, I'm going to take the natural log of 0.5 is 8k. Oops. Sneaky. K is going to be the natural log of 0.5 divided by 8. But I'll give myself one more line, or try to. There, I did it. So k is the natural log of 0.5 divided by 8, which is what? Natural log of 0.5 divided by 8, negative 0.0866433977. Makes sense that it's negative because it's a decay rate, right? So any decay, you have to have a negative rate, or k, I guess. Let's do doubling time. If an account grows by 6% per year, so now we've got a growth function, right? Compounded monthly. How long will it take for the account to double in size? Yeah. And so let's see here. So if we're growing, then usually we're talking about doubling time, things like bacteria and populations, right? We want to figure out what the doubling time is. Yeah. And so half-life, doubling time are two options. Okay, the account at time t is going to be the principal amount A times 1 plus R over, were we using K? Which is kind of confusing. Yeah, right? Thank you. Where K is now the compoundings per year. So here, this tells me that K is 12 monthly. The rate is 0.06, so R is 0.06. And we want for the account to double in size, starting at some generic A, right? Then we want it to go to 2A. So now I've got 2A is A times 1 plus 0.06 divided by 12 times 0.0, whoops, nope. 12 times t. You can do the same thing that we did before, right? If I have two things on each side of the equal sign, if I'm multiplying all the way across, then I can just cancel them. Technically, what we're doing is we're dividing over by a to one of the sides, and then a over a is 1. But I'm just going to slash them here, which means that I have 2 is 1 plus 0.06, and maybe I'll do 0.06 divided by 12 if it's something nice. It's not really, but 0.005. Let me just make sure. 1, 2, 3. Good. You guys probably know how to make it not do scientific notation all the time. Mine only does scientific notation, even for something itty bitty like this. I'm sure there's a way to fix it. I'm confident, but I don't know how. Anyways, get distracted. So I've got 1.005 to the power of 12t. Now, we could take the log of log base 1.005 because we've got our snazzy calculators, but usually what I would do is I would just take the natural log anyways. Right? It's a little bit more work, but we'll see that we end up in the same spot anyways. So let's take the natural log of 2. You're welcome to take any log that you want, right? And you'll see that you end up in the same spot. But I will show that I'm taking the natural log of 1.005 to the power of 12t, which I can rewrite as 12t times the natural log of 1.005. It's the log of 2. Solving for t can divide all those things over, but then I like to have it on the left. So then I have the log of 2 over 12 times the log of 1.005. This is the change of base formula, right? This is the same as 1 over 12 times the log base 1.005 of 2, right? From the change of base formula. From change of base. So, hello? What did that say? Exceed your whatever? Well, it's not exceeding my expectations, that's for sure. Okay, weird. Little intermission. But this is just a number, right? Natural log of 2 over 12 times the natural log of 1.005. They're all just numbers. And so we get, let's see here, log of 2 divided by 12 times the log of 1.005. I get a t of roughly 11.58131013. Years, because in this formula, t is always in years. So roughly 11.6 years. 0.6 years would be 7 months-ish, right? 11 years and 6 months, or sorry, 7 months, so close. Let's see here. Let me just make sure. Before I tell you. No. I'm trying to remember what the rule is. Oh, do you know the rule of 72?
Only 42.
I don't know the rule of 42. Oh. I should do that on my on the final exam. Just make all the answers either C or 42. Ben? I look up, everyone's hesitating. No, go on, guys. You've got it. You've got it. I could probably pull that off, and that would be pretty funny. It'd be a lot of work, though. Getting answers of 42. No, what's the rule of 72? Dang it, I can't remember. 6 divided by 72, and then the log of that. Nope. Something about 72. Oh, I teach it all the time, and now I'm totally blanking. I'm like the easiest thing. I got nothing. I'll remember for next day. It's a financial thing. The rule of 72. Okay, fine. Let's do this. $72 divided by 6. Does it work? 12. Pretty close to 12. Okay, I'm ready to tell you about the rule of 72. The rule of 72 is 72 divided by R percent. So in this case, 72 divided by 6 is 12, gives the approximate doubling time. Clearly, it's approximate. 12 years, 11.58 years, right, is what it would actually take at that compounding frequency and things like that, right? But it gives the approximate doubling time.
So on the exam, how many marks do you get for the rule of 72?
That's just a life skill.
What?
Rule of 72. You're at the bank. Yeah, you get all dressed up, go to the bank. No, you're sitting at the bank and they're offering you rates and you are trying to decide if it's reasonable for you. Then what you could do is take whatever the rate is, recognize that there's some wiggle room, right? But approximately however long you're comfortable with whatever amount you put in doubling, right? It could be $1 doubles to $2, right? 100 doubles, right? So whatever amount you have, how long you're comfortable with waiting for it to double, right? So it's just a life skill, not on the test. Well, maybe a bonus. Because I forgot the bonus on the last test. Let's see what I can do. You deserve a bonus. Okay. What do we want to do? Yeah, 12 years. Okay, well, I'll see if there's anything useful in here. Well, we already talked about doubling time, I guess. Pretty intuitive from the name, which is nice. Sure. A population of fruit flies doubles every 10 days. Yeah. Same deal. I'm going to assume continuous growth, right? And we want to find K. Sorry, R, because it's growing. Let's see here. F of X is A times 1 plus, that's not what we were doing. Yeah, I feel like I shouldn't have used continuous before, but it's nicer if they're all continuous. So let's stick with that. A times E to the K times X. One plus R to the power of X. No, you could still do it, right? Because you would have 2A is A times 1 plus R to the power of X. But we're given that X is 10 and A is going to cancel. You can solve for R. Yeah. Let's stick with this one. Could try both. Why not? If I have something like this on the exam, I'll be sure to clarify if it's continuous or not. I feel like these should all be continuous, but what do I know? I just work here. Okay. Doubles, same deal as we did over on the right-hand side, right? 2A is A times E to the power of K times 10. Right? This tells me that F of 10 is 2A. Right? We're now X is in days. We have 2 is equal to E to the 10K. Taking the log of both sides, I get the log of 2. Sorry, the natural log is equal to 10K. So K is going to be the natural log of 2 divided by 10. K is 0.0693147186. Maybe we'll do both. Scoot this over. I'll say this is for continuous growth. Oops. And this is for just, I don't know, regular growth. What's the word I'm looking for? Just an exponential function. I don't know. Let's see here. So I have 2 is equal to 1 plus r to the power of 10. Ba, 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 ba. Yeah, okay. I'm gonna take the 10th root of both sides, I guess. I guess, she says. Let me see here. 2 to the 1 over 10. All right. I'm committed. 10th root of 2, which on your calculator, you're going to do 2 to the power of 1 over 10, right? Is 1 plus r, which means that r is going to be the 10th root of 2, which is 1.07177346 minus 1. 0.07177346 Pretty similar, right? 0.072 versus 0.069. We have similar rates, regardless of how often things are compounding. Similar. This is a good question. If I make you do it both ways. Too many skills in one question. Too many. Or just enough. That was A. Just for practice, maybe we should use this, I'm calling it the regular growth. I don't have words today. Let's use this equation for B and C, just for practice. Use this equation for B and C. We want to know how large will the population be in 20 days. And so what we can do is we can write out our equation, f of t. We don't actually really need it, but that's okay. F of t is a times 1 plus 0.072. Let's just use the rounded value to the power of t. When t is 20, f of 20 is a times 1.072 to the power of 20. 1.072 to the power of 20. A times 4.016943351. Shouldn't have used the rounded value. Why? That should just be 4, right? 4 times A. And so this is from using the rounded value. Because if we know that it takes 10 days to double, then in 20 days, you've doubled twice, right? 2 times 2A, so it should be 4A.
U
a times the 10th root of 2 raised to the power of 20, and then you change that to 2 to the power of 1 over 10 to the 20, it's not that terrible arithmetic. It just becomes 2 squared. You get 4 exactly.
Nice and clean. This is okay. I'm okay with this, right? But if you had kept all your decimal places, right, then you would have gotten to 4, right? We expect this to be 4 times a, right? Since we doubled twice. Since in 20 days, we will have doubled twice. I'll do 2 to the 1 over 10 minus 1, and I guess plus 1 to the power of 20 is 4. Whoa. Do that. So just as long as you recognize that if you rounded, then it's not gonna check out completely, but I mean, that's close enough to me. 4-ish. How large will the population be in 45 days? Right. So now, 45 days, I've got f of t is a times 1 point. It's like I won't learn my lesson. I'll use the rounded value. You're welcome to try it with the exact value. I want f of 45 is a times 1.072 times 45. So 1.072 to the power of 45 is 22.84364177a versus using the unrounded value. You know what? The exact value for R, I'm gonna have to do it. I didn't store it the first time, and that was my biggest mistake. To the power of 45, I get f of 45 is 22.627417. Again, similar, 22, 22, times a. Does that kind of check out? Well, we had in 10 days, we doubled. In 20 days, we quadrupled. In 40 days, we would double the quadruple. Is that what's going on? I have to write it down. Don't want to. 40, how many times did I double? 4 times, right? So 8. Or 2 to the power of 4. Man, I'm just lost today. I'm gonna do it. F of 40. And I still didn't store it. 2 to the 1 over 10. Is 16. Okay, 2 to the power of 4.
It's 2 to the 4.5.
This?
This is supposed to be 45.
I know, I was just checking to see if this makes sense. Because, yeah, but the problem is that it's exponential like this, so it's not linear. And that's what it's meant to show you, but I'm just dropping the ball.
2 to the 4.5 is 22.6.
It's a lot of
Makes-
fives, we can all agree.
There's nothing every 10, and you have 4.5.
Yeah,
3 is 10.
yeah, and 2 to the power of 4.5 is 45 divided by 10. It checks out. I'm just not there mentally to check our answer. It makes sense, sort of. Put a smiley face there to really seal the deal. Oh, need my. I was just checking to see that because 45 would take longer or should be bigger than 40, right? And so we have the doubling time, so we can just make sure, okay, it's bigger than 16. And so this makes sense. Yeah. But didn't do a very good job. Let's see here. Or should we save it? Newton's law of cooling. Let's see here. He's probably got a fancy. He does. Didn't even need to write it. The temperature of an object, T, so that's the temperature, in surrounding air with temperature T, subscript S for the surrounding air, will behave according to the formula A times E to the KT plus whatever the surrounding temperature is, where T is time, A is the constant, which is the initial temperature of the object in this case, and K is a constant, and it's the continuous rate of cooling of the object. So we've got a turkey. A turkey is taken out of the oven at 165 degrees and placed in a 70-degree room. After 10 minutes, it's cooled to 150 degrees. We want to know what will the temperature be in 30 minutes, which means that we have to find the equation and then evaluate it at 30 minutes. And then how long will it take to cool to 100 degrees, which we can use the function for as well. So we want to set up this equation. First off, T of T. So the temperature at time T is A times E to the K times T plus the surrounding temperature. Yeah.
That's just the same fancy E from the.
Yeah. Yeah. Yes. A is the constant, which is the initial temperature. Now, if you're pulling it out of an oven at 165 degrees, we're going to assume that the turkey itself is also 165 degrees. And so this, I'm going to let this be A. It's placed in a 70-degree room, which means that this is my surrounding temperature, which is what it's going to be approaching. Right? And this tells us that F or T of T rather, T of 10 is 150. Right? So here A is T of 0 is 165. But what about the surrounding temperature? Let's not do that. There. Just keep it at A. Okay. Yeah, T subscript S, which is the surrounding temperature. So now I have 165 is our initial temperature, E to the KT. Now I don't know K, and we want to keep T as a variable, so we're trying to solve for K plus 70. We're told that T of 10 is 150, and we need that to be able to solve for K. So we know T of 10 is 150. So then 150 is 165 e to the K times 10 plus 70. Subtracting 70 from both sides, I get 150 minus 70 is 80, which is 165 e to the 10K. 80 divided by 165, same rules as always, right? We need to get the exponent on its own. So 80 divided by 165 is nothing nice. So just gonna keep it like that for a little bit longer, is e to the 10K. Now I can take the log, or I'm gonna choose the natural log of 80 over 165 is 10K, which means that K is the natural log of 80 over 165 divided by 10. So natural log of that divided by 10, I get K is negative 0.07239188392. I'm going to learn my lesson and store that in, I'll store it in A. I'll make a note of that here. It's more of a note for me that I stored it in A so I can retrieve it later. Makes sense that it's negative, right? Because if you pull things out of an oven, you expect them to cool off, right? And so that's good. So now we have our K. So I'm going to write just negative 0.072, but I'm going to keep all my decimals in my calculations. And so now I have T of T is 165 e to the negative 0.072 T plus 70. Now I can use this to solve What will the temperature be in 30 minutes? Presumably after you take it out, after removing it from the oven. Maybe I'm the only one who's, because we've got this after 10 minutes, but we just want to think about 30 minutes after we remove it from the oven. So T, oops. Oh my gosh. T of T is 165 e to the negative 0.072, but I wanted T to be 30. So I'm gonna do that and then go back in here and change this to 30. Stored in A times 30, and then e to the power of that, oops. Times 165 plus 70, I get 88.80624426 degrees. Is he using Celsius? 165 degrees Fahrenheit.
Yeah, that's the safe cooking temperature for most things.
Oh, wow.
70 degrees, that's room temperature.
I guess that makes more sense. Wow. Keep me on my toes. Degrees Fahrenheit. Maybe it was just wishful thinking. How long will it take to cool to 100 degrees? That's the same thing as asking, well, if I force this to be 100, 165 e to the negative 0.072 t plus 70, what is t? 100 minus 70, 30 is 165 e to the negative 0.072 t. Nothing nice, okay. 30 divided by 165 is e to the negative 0.072 t. Take the log of both sides, and of course, I mean the natural log is negative 0.072 t. T is the natural log of 30 divided by 165 divided by negative 0.072, but what's actually stored in A for me. So I get T is roughly 23.54888.421 minutes. Nice. All right, that's good enough for today. And also, I'm out of time. If you have any questions, let me know. Otherwise, I will see you on Friday. It's a little blip on Friday. Stop this recording.